Like I think that's a lot easier, and then I can
Yeah,
always edit it out.
that's fine. Yeah. Are you gonna get Stephen Bridges to do it? I'm just kidding.
So I think it's 4:10 now, so
Hmm.
we might have a few more to join. I think I would allow and then type
Yeah,
in. But feel
probably
free to
give like
share
10 more
your
minutes.
screen, and I'm gonna
Yeah,
try to stay a little bit quiet. And for those of you who joined, if you wanna show your face, would appreciate so that Brandon can see your reaction. That would be great. So if you
yeah,
can turn on, if you're in a place, you can turn on the camera, or if you're not tucked in your bed and trying to watch this, I mean that we understand. But if you can turn on your camera, and so that Brandon can see your reaction, they'll be really appreciated.
it helps a lot because sometimes I don't know if I'm talking to a wall or I'm talking to,
That's
you
right.
know.
Yeah, and then Brandon offered to come in person as
Mm,
well. But
yeah,
I thought that, we want to see the analysis from his computer that he's doing analysis. So I
yeah,
insist. And then also some of the students couldn't make it, so I can record it as well to help
yeah,
some of the capstones. So if you can turn on the camera so that Brandon can see your reaction, like do they understand or they even are they there,
yeah.
right?
It's kind of like,
That would
do
really
you have
be
headlights or not?
appreciated. Yeah, if you
So,
can turn on the camera, but I mean, if you're like hiding somewhere, we don't need to see you. But if you could turn
yeah.
on your camera, that'd be really appreciated.
See, did I do that? I did do that. Aha. Okay.
So
Just
those
making
who
sure.
joined the later, they're just signing with Brandon Mack, and he's with the Gresham Smith. I'm gonna let him introduce himself so that you can hear the whole history with the UGA.
Yeah.
So,
So,
go ahead,
yeah. All
please.
right. So I'm Brendon Mack. I'm a formerly a assistant structural engineer, more on the bridge design side. Um, Sometimes I'm project manager. Days I'm drafter, designer. Some days I'm, hopefully a fly on the wall, but most of the times I'm a structural engineer. So, graduated from UGA back in 2017. It was a much different building at that point, So, uh, due to lots of love and TLC on the building, that we now we all get to enjoy a lovely building. Um, it's not creepy at night anymore, which is great. So, um, back in, so I have about 7 years experience now. Um, Basically do bridges for a living. So I'm going to take you through a project that I did back in 2022, only about 2 years ago, when my company, previous company, got a call from City of Atlanta when a bridge was on fire. I guess both times. So, Cheshire Bridge has kind of been a lovely little part of my life that I keep getting paid for over and over. Where is this thing? I'm going to take you on into Cheshire Bridge. If you don't know where it is, it's on the northeast side of Atlanta, kind of in this location. Of course, this is the finished product. You got a lot of businesses here. The main thing that's kind of different about my structural engineer experience is I kind of think about the whole site and everything and the impacts of the community that do follow that, as compared to if you're in vertical construction or vertical engineering, or vertical construction, vertical structural is, you kind of think more about the building itself versus I think about the site and everything that's included. And unfortunately, weather events also include that as well as people. So kind of a couple things when you think about a bridge design is the different impacts you're going to have. So for example, if you see on the side, you have some businesses over here, you got a little greenhouse over here for like Pike Nursery. You have the EPA right here with their different sensors and um, systems in place for flood control. You have schools up the way, you have hospitals, you have public agencies like firefighter, police force, stuff like that. And you really want to make sure that when you're doing a design to accommodate your community. So definitely not structural analysis, but keeping that in mind, that was kind of the big thing. City of Atlanta came to us, basically saying we need a bridge ASAP, and it just burned down. And when a bridge reaches about 4,000 degrees, it kind of melts everything in between. The previous bridge was in about 1930s or so. It was supposed to be replaced in the late 90s. This one, of course, is brand new. Due to funding and grants and such like that, we went ahead and said, we're going to replace this bridge, close the road, which was not super preferred, but we couldn't really save the structure that was on fire and do the whole loads analysis and everything like that. This was technically a design build project, meaning that you design it and build it at the exact same time. On the engineer side, it's a little bit tedious because you have to design it from the ground up versus in a traditional design, you design it first, then you bid it, and then you build it. So instead of a top-down design, you have to design from the bottom up. So I'm gonna show you the plans. All right, so at the end of the day, you kind of have to think about your span arrangement. You kind of have to go over the creek bed. So if I go and I do, I'm just gonna grab a different map. So kind of like when you're doing a typical design, you kind of want to think about, can you span the creek? Also, the Environmental Protection Agency says that we cannot put piers in the water if we can help it. So we do have to span that. Another type of engineering that we do have to conduct in this analysis is a hydraulic analysis. So thinking back to your fluids and your hydraulics, you have to think about conduit flow. And is it turbulent? Is it laminar? What's the effects? If this area floods, where does it go? So if you zoom out a little bit, and I'm actually going to change it to, well, thought I was. Here we go. I'm going to do the train. So if you look out at this thing, so this is North Peachtree Creek. You have the creek running down this way, and you can kind of think about when this thing floods, how's it going to react? And you have to make sure as a structural engineer, when it floods, concrete, of course, does great underwater. Don't get me wrong, but also what doesn't do good underwater is the cars that go over it. If you think about bridge engineering, you're making a fancy table for cars. So at the end of the day, you have your Hot Wheels as a little, 5-year-old kid going across the table, can handle it. If you flood the bridge deck, the cars are probably going to go wild. So you got to make sure that the bridge is above your 100 or 500-year storm. So little background history on it. So at the end of the day, we kind of came up with this design for a 3-span arrangement bridge. Just for simplicity of design, you can kind of tell that in the elevation view, and this was on purpose, we're in a design build situation, you want to beef up your foundation to accommodate your beams and flanges above and also your cars. So in today's form, it looks a little funky because kind of have a beefed up foundation, but you have tiny little beams going across. That was on purpose. This isn't a seismic zone for City of Atlanta. Also, the soil was not that great either. Most of the Piedmont region is just not that great because as the creek is washing through, it's washing away all the soil that actually protects your foundation. So, just to kind of go over the creek, I know this is a lot of little lines and call outs, but this is kind of the approximate banks of the creek. We tried to ensure that we were kind of outside the banks or at least close enough. Because this was design build and we had to make a fast decision within 4 or 5 hours or so, made a 3-span arrangement. At the end of the day, this could have been a 2-span or a 1-spanner and just go really crazy and boost the road up. But in that case, it just didn't happen. Furthermore, there's some more general notes of your facts and figures. You have your bridge consists of drainage data. You have your really lots of different other things going on. You have your, this is kind of like back to your hydraulics class, your 50, 100-year and 500-year storm. Formerly, this used to be called the infinity storm. This is your worst case scenario. You have your discharge rate, you have your mean velocity, all that stuff. The model that I'm about to show you does include that. Just to kind of that scenario, that worst case scenario, if everything gets flooded, then you're completely still okay. This is the traffic counts from your traffic engineers. Since you're civil, you're going to be dealing with all types of civil. So your project partners are probably always going to be project partners in some kind of way. you know. Um, we posted this at 55 miles an hour. Probably should have been 45. Do people drive more like 80 miles an hour? Yeah, that's up to them. you know. Fun fact of the day, if you drive your car along a bridge with a barrier, you are only protected up to 45, 50 miles an hour. And if you drive over 50 miles an hour, it's not ensured that you'll stay on that bridge deck. Just letting you know. So just, you know, go the speed limit if you can. And then all your different notes telling the contractor what to do between what specifications to have, shop drawings, reinforcement steel, what type, um, clearance of steel being 2 inches at all times. That's just kind of a rule of thumb. Existing bridge plans, dowel bars, groove concrete. There's a chain link fence on this. Make sure people don't like fall off. How do you weld? You should have a certified welder from Georgia, nowhere else. Sorry. Yes, we are taking out the bridge. No, there's no salvage material, et cetera, et cetera. And a little bit of quantities that can, of course, can change. And then what kind of concrete we're using in our design. So we specify this way ahead of time. And we tell you that, yes, your superstructure design, meaning your beams from your bearings all the way up to the bridge deck, is 4,000 PSI. And then, of course, everything below, you kind of have a different specialized design. Your reinforcement steel is always in bridge world is always going to be 60,000 PSI. Your pretension strands are always going to be 270,000 PSI, just for this type of design. You do have to keep tension in check because our strength, no pun intended, is going to be compression. So this kind of your little layout. Again, you're making a fancy table for cars. So how do you do that? You put beams across the bridge deck. Not to get into too much, but we kind of have to tell the contractor everywhere everything goes. This one was a little complicated because it's curved. On a bridge, everything is unfortunately curved on the geometry, but everything is straight underneath. You can't make curved concrete, unfortunately. You can make curved steel, although. So this is kind of our typical section. If you think about a typical section, I think of it like French bread at the Publix bakery. You take a little slice out, and there you go. You're looking at it. It looks great. It's ready for butter and peanut butter. I'm a peanut butter fan. Um, so you kind of look at it. We're kind of detailing out a couple different types of utilities. On this bridge, we have a 12-inch water main, and then we also have future conduit. In this situation, we had telecom. We just put conduits out. Hopefully they'll put it in one day, but we just had to accommodate. So sometimes you have to accommodate for future use. City of Atlanta definitely wanted an 8-foot sidewalk with a bike lane or a shared shoulder bike lane on the side. That's just kind of for future expansion later with the Atlanta Beltline coming through. And of course, your typical 2 10-foot lanes on each side to accommodate traffic due to over 50 miles an hour. We have to do that. That's from the AASHTO Green Book. So if you're over 50 miles an hour, usually you have to have 10-foot lanes, at least. Highway is, of course, 12-foot. Same thing on this side, same exact thing. Symmetry is your friend when you're doing a bridge, especially bridge analysis. So if you can do it once, you can do it once. If you do it 3 times, probably not going to be that efficient in your design. So any way you can make it more symmetrical, the better. Of course, in this one, this is a lumen conduit. It's a little telecom as well. Don't know why they just wanted inserts that way. So to this day, I have no idea. Because we're in design build, we decided to do steel diaphragms. The diaphragms are for horizontal movement. So when you place the beams right on top of your cap when it's built, and I'll go more into that later, you want to make sure that the beams don't sway back and forth from wind, water, whatever. This happened on a bridge site where you're kind of modeling for the previous and to the built environment. So if let's just say you put the beams up, and you get a bunch of rain and everything floods, you want to make sure that your beams don't sway back and forth and fall off the bridge cap because that's happened. which each beam is, I might be wrong, but I think each beam is about 150 to $250,000. So you don't want anything bad to happen to them. So, um, calling up the fabricator saying, "Hey, can you make another beam for me?" is really not a bad. It's a really bad conversation to have. So, um, so diaphragms are here, and then you get to edge beams. So, and this kind of gets a little finicky. An edge beam, an end wall, and a diaphragm all have the similar purpose of keeping everything in line and keeping everything in all conjunction with each other. To be specific, an end wall is at the end of the bridge. It's an end wall, literally. So engineers weren't that clever in making this thing. A diaphragm is in the center, mid span of each span of the bridge. Not to have a tongue twister, but it's at the mid span. And if you think about an edge beam, so we have the end walls on either side at the end locations of a bridge, a beginning or an end is at the same spot. So an
And
end,
can you
yeah.
tell students a little bit more about diaphragm? They just learned that the diaphragm as the floor.
Oh, okay, yeah, yeah, yeah. So you have floor beams, which is very specific, and then you have diaphragms. If you think of, I kind of think of a diaphragm as what keeps, so you're standing up and your diaphragm goes out, you usually hit the floor. So you usually have to, keep yourself up. It does the same thing for beams and its bridge itself. So if you think about the anatomy of a human body, it does the exact same thing for a bridge, just to kind of put that concept together. Um, and and I guess what, Giuseppe, can you, well, I don't know if did I explain that
So
right?
the diaphragms in this case is the four beams that they see, not the, it's a letter load path, not the floor in this case. It's
Yeah,
really referring to these beams, four beams that Brandon talked about.
yeah. And if you kind of think about a diaphragm, you're kind of making a concrete sandwich in a way. You have your beams going all the way down, and then you have the interlocking pieces all in between. And you kind of have to think about anything that's lateral movement, you have to keep that in mind, because if a impact loading is always kind of a thing. If you have an 18 wheeler going across your bridge is going to sway and bend and deflect and everything else. So you want to make sure those diaphragms are all put in third sections all the way down. So kind of like in this design, like if you go from begin to end, I have an end wall, go midway through, you have a diaphragm, and then you go to the next span, which is right here, you're gonna have an edge beam. All diaphragms, the exact same purpose, they're just a little bit different. So if you go to span 2, you're going to have an edge beam, you're going to have a diaphragm, then you're going to have another edge beam. And of course, the end, you're going to have an edge beam, a diaphragm, and an end wall. All function very similar, but it just depends on where you are along your bridge deck. So, so kind of like on here, if you kind of can notice, so an edge beam, so if I go in between two beams, you're going to have two number 5 bars on top and bottom, and it's going to go in between each beam to kind of keep that lateral movement in mind. As compared to if I go down to an end wall, it's going to be all the way down. It literally physically actually works like a retaining wall, keeps the soil back, but it also keeps the beams interlocked in between each other. So it kind of has like a multi-purpose. If you really love a nice good cut section, this is kind of what an edge beam looks like. So you have a beam coming in, another beam coming in, and it kind of fits in between each piece. So when your car goes to dump, to dump, to dump all the way down, your car is actually going across this expansion joint across your edge beam, if you kind of think about it. Whereas compared to the end wall, meaning this piece over here, your end wall, you kind of have bars coming in, you have a beam coming in sitting right here on top of your end bent cap or your abutment. The vernacular is all a little different, but it's keeping the soil back, it's keeping the approach slab on there, but it's also keeping the beam all in place too, so it doesn't sway back and forth from lateral movement. So if you have those fundamental theories there, it all works out just fine. Um, the nice thing is that most DOTs, they standardize these kind of details. So the nice thing in the bridge world is it's like a copy paste. So just kind of depends on what kind of beam that you're kind of using. So of course, we love all kinds of details, but I'm going to kind of skip this. This is kind of more of the superstructure details. You have fencing, you have sidewalk, all kinds of different things. And then you have your different hangers. So kind of like this is our diaphragm piece. We're specific on what kind of steel pieces that we're using. If you want to look in yours, I call it the steel Bible, your steel manual, latest one. We used a 13 by 40 MC type section, meaning two L brackets together, and it's one big giant piece together. So the beam itself, here's a beam, another beam, you kind of put a through bolt through, another through bolt, little L bracket, and then you have this big metal piece going through. You can kind of visualize that. So, of course, we got our framing plan and all that fun. The short sections, we have type 2s, more type 2s, and guess what? More type 2s, because we're going to make this easy on us. So because symmetry is our friend, we're going to use small little beams on a giant structure. Why not? And of course, our bearing pad, if you go back to your section, just kind of giving the anatomy of this bridge, at this section, so you have your bridge deck, you have your beam, and then you have your bearing, and then you have your cap. So if you go back to that, I don't know, I might age myself 10 years, but if you go back to the age-old, branch on a tree, tree in a hole, and the world goes around, back to that song, that's how bridges work, unfortunately. So you kind of have to piece it all in different pieces. So, um, any questions so far? Just make sure.
I did have one question actually.
Yeah, go for it.
1 second, please. Let me see if I can find it in my notes.
Yeah, yeah.
Where you had shown the future paving allowance, is that um the design requirement if the bridge were to be repaved?
Yes, yeah.
I see.
So in its future, it's going to be standard says a 1/4 inch on all bridge decks. So that's going to be your 0.30 kips per linear square foot. Sorry.
Mm-hmm.
Yeah. Sorry. I was like, I was good. Check your units every single time as a structural. So, you know, but that's kind of they'll do that every probably 20 years or so
Mm-hmm.
approximately. When they actually get to it, we'll specify 10, but they probably will get to it in 20 just with
I
funding.
see. So you'll design and analyze with the paving already
Yeah.
pre-placed onto the deck. I see. Okay.
Yeah, yeah. And we'll get into this more. So as you're putting more weight on the thing, since
Mm-hmm.
it's a pre-stressed girder, it's going to come in and it's already going to be kind of bent already. And we'll go into that later on with the D dimension and the haunch.
Mm-hmm.
But as you're putting more weight down, it'll kind of slowly creep down to hopefully like a frowning face style, have that
Right.
nice camber. If you have a smiley face, believe it or not, it's actually bad. So
Mm.
yeah,
Thank you.
cool. Did anyone have another question? No? Okay. All right. Okay. Hopefully I'm not losing y'all. So yeah. All right. So Ash 2 type girders. And we all have different types of beams. Dr. Zeppo can use any beam possible on any design, anywhere possible. So these are kind of very small beams. They're only 3 feet tall. So if you have a medium-sized dog, it's probably about that high. So when they get shipped in, they kind of look like as tall as my as tall as my Honda Accord. That's about it. So um, as you can kind of see, as you kind of put this thing together, I'm actually going to go over here first. You have kind of a midpoint section. So this section is from straight into the center. And then this one is going to be seen on the very end. And you'll kind of see that in the model as well. As you can tell, these pre-stressed strands are going to be draped from the mid section of the beam all the way to the bottom section of the beam. As you see in the midpoint, there's no strands in the middle. So, and it'll kind of look a little bit like this since in the midsection. So of course you have, this is for tension and compression, and then you have your anchorage reinforcement around this area, kind of going back to your materials class. And then kind of towards the middle, as you can tell, your spacing gets less and less. That's on purpose, to kind of get that nice moment curve going on. back to, I think y'all still call it strength of materials, right? I think, okay. Some universities call it mechanics of materials, and I always get really confused. And of course, all the different specifications, and you'll have, hey, per fabricator, make sure all the chamfered edges are between this tolerance, and make sure the bearings are for this tolerance, and make sure everything is good. As a structural, you'll give it all to the fabricator, and the fabricator will come back and say, I can build it better, and that happens every single time. So, as long as it meets your criteria, it's completely fine. So, and of course, the different diameter holes for the diaphragm itself, you kind of prefab that in. And also, don't be deceived by this. I actually had a question on this a little while back. Don't be deceived. They're just PVC pipes with concrete around it. You can build this at home. I wouldn't recommend it, but you can build this at home. You know. Another thing, and I'm actually going to go to span 3 on purpose, just because it's a little easier. At the very end, you're pre-stressing data. You're going to have your design as follows. You're going to have 28 half inch, 0.6 inch diameter, low reflex strands all the way down. And make sure you have your release strength as 8,000 PSI. Your last and final strength is going to be 8,500 PSI. And then of course you have your allowable tension per your design is 553. Just telling the fabricator ahead of time that if anything kind of goes outside those limits, do not give me that beam. So, and you can reject beams. Of course, from the top strands including, you have jacking force. So when I say jacking force, you have forms on left and right. They pour the concrete in the middle with all the different rebar cages in between and all the pre-stressing strands, and they're going to physically jack it up to 1,230,404 pounds. If you can kind of think about how much that is, it's a lot of pounds. So just being honest, and then including the top strands, the net pre-stressing force at the loss range. So as the person cuts the ties on the pre-stressed strands, it's going to release a little bit, and it's going to actually lose a little bit just because the material is not there yet. Turns out you probably get all that theory in there, to be honest. And we probably won't go into substructure just because of time, but if you love to read rebar, this is the design. I'm going to go to span 2 or intermediate bent 2 on purpose, just because this is hard to read. I didn't do the best at drafting this. So in the ground, you have your caissons or your drilled shafts at 5.5 feet on diameter. And then on top of that, you have columns, and then you have a big giant cap. If you look at beam design, if you look at a column, it's a beam. If you look at a beam, of course, it's a beam. If you look at a lot of your fundamental structural concepts, if you understand beam theory, the whole thing makes sense. You kind of understand your moment and shear curves, everything makes sense. So just if you keep that in mind, everything kind of coincides with each other. Of course, you have the bird's eye view, you have the cut view looking right at it. And then you have, if you want to cut it open, that's what the inside of the sandwich looks like. If you want to look back at your concrete analysis and you have your stress block, this is exactly what we're talking about. All right, so I'm gonna go to the model, and it looks a little daunting, but anyone can do it. If I can do it, anyone can do it. Let's see, and I want this one. So if everyone could remember what this looks like, it's gonna be exactly the same thing. All right, actually, I'm gonna go back one. All right, so we're gonna do span 3 just because it's easy, and we're gonna win this race because it's over there. If you kind of can tell these plans, so if you look at this, it should look like that. if you look like, oops, if you look at the typical section with the beams like that, oh look, it looks like that. So this program is called Open Bridge Designer. This kind of takes a formal approach at modeling. If you kind of can tell, it's almost just based off like a STAD, almost like a STAD program. You have finite analysis built in all in here. It's very user friendly. It's made by Bentley Systems, which is a love-hate relationship for me because the customer service kind of is you know, but their manuals and their engineers and all our nerdy people in the background do a really great job at making this stuff happen. Also, if you can tell, which makes me very happy, you can kind of see all the pre-stressed strands in there too. It's kind of cute. I don't know, kind of cutesy, very demure. I'm gonna look at the side here, so you can kind of tell if you look underneath, I think that kind of looks like a deck section to me, like a deck plan. So if you look underneath, everything's kind of there. And of course, over here, you have your kind of end bend cap. So when I say cap, it's a cap. Everyone likes a visual. So this is, in this case, we're going to be modeling, we're going to assume that the truck can be anywhere along your bridge deck, and placement of your placement of your truck can be on top of the sidewalk as well as on there. So kind of like back to your typical section. Your conservative design is going to be a truck can be here. It can be here, 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 all the way over here. So worst case scenario, we're probably going to have probably about 6 trucks just in case. So, all right, so let's get into it. Pre-stress design. I put in all my sections, unfortunately. It doesn't like it. So this is who created it. So kind of need to define everything. So 72 feet wide and some change. Gutter to gutter is going to be 70 feet. This is an assumption, of course, including the sidewalk. I have to say that over and over because some people get, a little bit confused on what I'm trying to do. We are at a slight skew, 1.25 degrees over. We do have a parapet, so meaning a parapet's going to be 1 foot 1 inch, so 1.2083. Lane data, so this is actually assumed by the program, so we're going to assume that we can put 6 trucks side by side all the way down. If you look back to your design truck, does anyone know what the design truck is? Anybody? HL, anyone? Don't be scared. It's not 50. 93. So HL 93. Okay. So our HL 93 truck, which is basically your full-sized U-Haul when you move from UGA to your full-time job. Or if you don't have to move, that's even better. So it assumes that you can put 6 U-Hauls all the way down. Our lane width is going to be 10 feet. Our deck thickness is going to be our pre-prescribed 8 inches. With a sacrificial of 0.25, that means that's your wearing surface. And then haunch thickness, we're going to talk about it later. We assume it's 0 because there's a bug in the program. So since you have to be knowledgeable of the program, you have to input everything, but also be knowledgeable of what it does. We have astrotype 2s all the way down at our design spacing. And then we have, of course, our calculated overhang. Since we are along a curve, it might vary just a little bit. Yeah, that's about it. You have your precast length, you have your release span, and then you have your bearing to bearing. Your release span and your bearing to bearing is going to be the same. If from the fabrication yard, from bearing pad to bearing pad, if your beam is bigger than that, it's not going to fit, unfortunately. The next part of the program is that we have to get all our materials in there. So that's your material science. So we're assuming that our girder release at strength of 8,000 KSI is going to be 153 for your ASTO LRFD code. Girdle final, of course, is going to be 8.5 KSI, 154. And then, of course, your deck is at 4,000 PSI at 150 pounds per cubic foot for your for your weight. Your elasticity, this is also calculated by the program as well. Make sure you use that 120,000 square root of da 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 da. It's gonna be what's going on. Your Poisson's ratio is going to be 0.2. Your thermal coefficient is always going to be the same. Elasticity, of course, is about in there. And then your F of Y of steel is always going to be your 60. Okay. This is going to be draped. So our depressed factor is right at 5. We're just depressing it right at the middle. This can vary. You can actually change it from 45% all the way to 35, depending on what you want to do in your design. Next piece is going to be, this is just the type of low lax steel that we can use. We just kind of use this in our design. All right, loads is like the part that's a little hard. You have to kind of get everything down from your telecom to your conduits to your hangers to your sidewalk, left and right. Your future wearing surface, of course, is going to be your 0.03 for that magnitude. Then of course you have the haunch, which is going to be later calculated. You kind of do that iterative process back and forth to kind of fine tune that idea. You get your left and right parapet. You got your overhang added slab because we just had to beef up the slab on the exterior. And then your SIP, which is your stay in place forms. You put that metal decking above to keep the concrete from going down, and it stay in place. When I said earlier about the diaphragms, this is also calculated. So you take your cube of concrete and then you kind of substitute down to your load of 0.2 kips or 0.4 kips, depending on where you are. If you're on the exterior, of course, you don't have a diaphragm on the other side of you, so only 0.2. Interior, it's going to be 0.4. Remember, you're getting half of each side. Also in your process, you're going to also include your live load deflection. You're going to keep your design lane, design tandem, design truck. This is just a bug of the program. It's just it's a combo, fortunately. All right, and I already kind of ran this earlier, but we'll run it again.
And
The nice thing.
Three things some students might not understand is a haunch and release strength and draping. So if you can focus on explaining that, it might help some students.
So your haunch is going to be, and I wish I had a better section, but your haunch is that little itty bitty triangular piece on top of your beam. When you put your beam down, unfortunately, it kind of deflects and kind of goes around a curve as you're going from point to point. We are assuming a simple span kind of analysis here. So this over here is not going to stay the same at midpoint. It's not going to stay the same on the other side too. Some states call it haunch. Some people call it D-dimension. Some people call it coping. Just kind of depends on where you are. And the drape, you said draping was another one?
Yes, draping and release strength.
So so draping, so if you think of it like a tablecloth, you know, kind of throw it in the air and you kind of has that little curve on the way down. That's what you're doing from point all the way down. So you kind of in the yard, you're going to have from point to point. So you kind of go from midpoint of the beam all the way down. And that's really to counteract that compression tension relationship. It's more of a, for me, it was on the job training, but overall, it's if you kind of think about it, as you're beefing up your section, the more you go up, the more it can take. So if I took these all the way up here, it can take more, if that makes any sense. Release strength. So release strength is basically from the yard to the site. It has to break at this amount. If it's if it's too low, the beam will just fall apart. If it's too high, it also will just fall apart. So you kind of have to adjust between the two. So if your concrete strength is too low, it also won't take its own weight sometimes, where if it's too high, the anchorage zone just explodes, like physically. It'll just crack, you know. Where final strength is going to be your final condition, final state, final everything. So after your 28 days of curing, plus then some, that's going to be your final design. So that's when you put the deck on and everything. Does that make
Thank
sense?
you. I think the student will see the strand pattern in the analysis model.
Yeah. So in the analysis, so if you're a number nerd like myself, you can kind of go from beam to beam. So let's just say I want beam 6 and I want the moment. Oh man, it's right in the middle at midstand. So that's going to be your max moment at beam 6, service 1, boom, done. And if you can kind of notice, and I would hope this is the case, over here and over here is the same number. If it's not, we have really big problems, you know, and then you have a bug in the program. Also, if you notice that the midpoint is going to be the max moment, you know, please make sure, you know, so I would say go to like service 3, just make sure deck at minimum, and just kind of check your numbers, just kind of making sure that that makes sense. If you see a ridiculous number, probably just go back to your inputs and then start again just to make sure everything kind of glides through correctly. So not to bore you too much. So here's kind of your beam. This is your full section of your beam, and then you have all your orange stirrups all in the middle. And from anchorage zone side to side, and then it kind of spaces out towards the middle. You don't need as many towards the center as you do to the sides, just because of your moment and your shear relationships. So, all right, so if I do, and so in structural world, by the way, this beam and this beam should come out to about the same, just being honest. This one and this one should be about the same. And you kind of can go from there. I'm going to just take the second beam to the center. So initially you'll have your computed stresses off your program, and then you'll have your final stresses. These are going to kind of be your limits. So you have your final stresses, and this is telling you, hey, at compression, this is your limit right here. Final tension, it should be pretty low. This is your limit. So for this specified inputs with your concrete strength, with the amount of steel that you provided, that should be the limit. And you can hand calc it. I prefer to use the computer to check me, but I still hand calc it. So final 2, you have compression strength, and of course it's going to be a little less on final 3. This is usually you'll play around with it a little bit. So let's just say, let's see, it's gonna fulfill. Well, I was gonna break it anyways. So the nice thing about structural is that you can actually break your own stuff, which is great, without actually breaking it. Let's see, it's gonna do it. Nope. 1 second. Nope, it's not gonna do it. Hold on. So the hard thing with these coded programs is that sometimes they just break. Does anyone have any questions while my computer figures out what to do?
Any student who took bridge design and had to do hand calcs, and the software just did it for within a minute. They go through all his PCI design, bridge design
Yeah.
manual, and do the problem one by one.
Oh yeah.
So they understand the whole process, and they see the software can do it in no time.
Yeah. Hopefully. No, it's just not going to do it. Okay, that's okay. All right, so
It's good. Doesn't want to break.
yeah, I've been running the computer hard all day, unfortunately, with different loading and everything. So, like for example, if you take out, let's just say the top 2 strands, which I love to do, it'll kind of show you that your limiting stresses on your final is going to always probably break. Where if you take all your drape strands away, usually you kind of need it. Also, another tip for your pre-stress design, if you kind of think of a cup, you fill it up all the way and you go into the bottom flange. That's usually how you do pre-stress design. The bigger your bottom flange is going to be, the more capacity your beam usually has. So bigger beam, bigger problems, unfortunately, but it also can take on more loading as well. As well as, so you'll look at your rebar pattern. So based on the inputs from this design, the loading included, with everything and all the inputs, it'll say you need this much. And you kind of like a little bit of a moment curve going on. And you'll have required versus provided. So you always have to be above this curve, of course, to provide enough strength from your reinforcement. And that's kind of your stirrups all in the middle. The nice thing about this program is that you can auto design it, let's just say. Probably not going to make it. Probably have to like beef it up on some sides. Let's just say, okay, so I'll put to number 6s. Okay. That sounds very nice. This makes it almost too easy, just by the way. So there's a lot of auto design features in here. It only gets you to your starting point. It doesn't get you to your ending point. So you kind of have to fine tune back and forth. And that's really all I have for structural analysis. I kind of took you through the plans, through the area, through your beam design, your inputs, kind of what you're looking for, your AASHTO codes, your GDOT structures manual, and then kind of down to your final huzzah on the beam design and kind of like where you're kind of leading to. Does
And
anyone
what
have
about
any
the
questions?
substructure design analysis? Like, what do you
We
generate?
can. Oh, so generally, so starting point for usual most stop structures I do, I usually do a 4x4 foot cap with a 3.5 foot column, either diameter circular or square, with a usually a little bit bigger of a caisson. So I'll just say like 4 foot. This one had a lot of uplift and the soil wasn't that great. So the geotech kind of told us the soil's not great. You want a lot of stability. It's also in seismic. Want to make sure you beef up your caisson just to make sure it can take the loading from below and above as well. See, so, oop, let's see, actually, just kind of grabbing a substructure.
And there's another question from Muhammad about post tensioning and diaphragm.
Yeah, go for it.
Muhammad, do you want to ask your question?
Yeah, actually, I'm a bit interesting regarding the pre-stress you were talking about. So, have you done any post-tensioning beam design? Then, how will you include the effect on diaphragm while doing the post-tensioning?
I've only done post tensioning one time, and it was with a PESE very certified person. We don't usually do a lot of post tensioning, at least in Georgia.
It's in
Yeah.
Florida, maybe.
Florida, yeah. I think I've checked, like on the 425 project, I checked their reinforcement and their design to do the post tensioning for the rods that go in through the beam. And I've also checked like process to do it, but I haven't actually physically designed it just because it's kind of a rarity.
Okay.
Okay.
And he's asking about like included fact on diaphragm while tensioning. Maybe he's a little bit confused about what's being tensioned, what diaphragm is. Maybe I confused them.
Oh, yeah. So either way, your diaphragm is going to be separated from your beam. So you're going to fabricate your beams post-tension or pre-tension. You're going to not mail them, but not like the Postal Service can take it. But I don't just call it FedEx. But you get it to the yard, you fabricate it, you put all the pieces and parts together, and then you fabricate to the site and ship it to the site. When your beam is completely there and on, then you put your diaphragms around it. I guess if you think of it, it's kind of like giving your beam a nice hug, until your bridge is completely built. Now, I will say when your bridge is built and completed, usually the diaphragms are not super duper needed. It's nice for lateral support, but it's not necessarily needed after construction's done. We just don't take it out because it's usually easier just to keep it there.
Yeah, so diaphragm was one of the beam, the one member that you attach for kind of stiffener. I think that might be easier
Yeah,
way to understand. And
that would
sometimes
be the
the
best way.
X-bracing, I think Brendon was showing you this member you attach between the girders provides
Yeah,
stability.
and usually, structurally, and just to be honest here, um, when you're constructing a structure of any kind, usually it needs a lot of bracing until you're completely done with it. So let's just say you're making a building and you see all the different stage construction parts and pieces. Usually there's a lot of pieces and parts to make it all sway and everything correctly to build that structure. Bridges are exactly the same way. So if you look at kind of how a parking deck is put together, bridges are pretty similar. So next time you park the car, look around, so. Is there any other questions?
Can you tell us a little bit more about your company and any
Sure.
recruitment plans?
So yeah, so I'm gonna give my quick spiff. I'm not really good at it per se, but so I guess royally, we are Gresham Smith. It was founded about probably 75 years ago from two architects out of Nashville, Tennessee. Their bread and butter was hospitals. Now we've gotten into all different sectors. We're kind of put together almost like a Google, where we have a bunch of different markets as different pieces and parts of the company, but we're under an umbrella term called Gresham Smith. So I work under the transportation umbrella. So that would include bridge, hydraulics, roadway design. You have traffic design, you have SIGOps, you have embed employees, you'll have you'll have environmental, you'll have ecological studies, you'll have mechanical, you'll have industrial, you'll have all these different markets all included under one umbrella. So a usual day will be all different types of every type of engineer that you could possibly imagine. Most of transportation is a civil per se, but at the end of the day, uh, sorry, seeing the chat go. Oh, thank you. So, we kind of do a little bit of everything. Recruitment opportunities, we're supposed to expand and doubling in size by 2030. It's a really advantageous goal, to be honest with you. Makes me a little nervous, but I'll be around because I'll be hiring bridge engineers, structural engineers, vertical and horizontal. If you want to do your SE exam, um, we'll do everything from environmental to civil to mechanical, electrical. We need them all. So we kind of do a little bit of everything. If you're a structural engineer, that's more onto the vertical construction side. I mean, we're kind of proud of this, but we're building Madera Parkside by Piedmont Park. That's our first residential building in Atlanta. Most of the bread and butter is more in Tennessee and a little bit in Kentucky. We are based in the Southeast, and yeah, so kind of do a little bit of everything. So if you see me around, we're probably hiring. So.
And the office is in Alpharetta, Georgia, right?
Yeah, so we have
I got
in
the
Georgia.
address. See if that's the right one. I put it in the chat.
Yeah, so we have three offices. One's in Buford, one's in Alpharetta, and then one's in technically downtown, but we call it Midtown. It's right on the line. So we have 600 West Peachtree. That's the GDOT building. Then we also have Sanctuary Parkway as well. Yeah, actually, yeah. That's our Alpharetta office. Really, really, really pretty kind of place. And then Buford, we're technically the building called the Water Tower. So we provide services to Gwinnett County Water and run their water treatment facilities. And we also may have designed their building as well. So, yeah, and all their different laboratories and stuff in between, because they have to test the water I think every other day, something like that. So does anyone have any questions about Gresham Smith?
One of the questions, like which offices have vertical structure positions? I guess
Yeah.
bridge structure, vertical, anything.
Yeah. So most of our vertical group is in Nashville. We're kind of sparse in between. We have Chicago, we have Denver, Nashville, and I think we have one person in the Midtown office. So we're kind of sparsed all over the place. We're kind of hybrid, remote first, but then come into the office as we need to. Like personally for me, they say I should be here 3 days a week. It's probably more like 2, you know, just depending on what location and what site I'm going to be on. So yeah, so vertical wise, if you're interested, I would say definitely apply. We're always looking for good people. And another thing too is that you don't have to be certified to maintain that kind of a position. Of course, that's part of your career. You should definitely get certified in your state on where you reside, but it's not like you have to have it as an entry level. Of course, pass your FE.
Excuse me.
Mhm.
Hello. In payment engineering, so we calculate the load in different criteria, right? Almost here also you are dealing with the traffic. So
Yeah.
why here you are following the most traditional way rather than going for the payment engineering approach? Is there any different special reasons here?
It's I'm gonna give you an answer. It might be vague, unfortunately. It all depends on your situation. So for example, if like usually in the sense we usually calculate it on the traditional sense, just because that's what the codes and tell us what to do. If you do find yourself in a situation where your traditional code doesn't apply, or you have a gut feeling like if you're going to sign and seal, you want to make sure that this thing stays up for. So the design life, for example, of this bridge is 125 years, which in longevity wise, probably not going to be around when this thing finally fails, per se. Um, and usually you kind of give that idea of um, if you uh, if you find yourself in a situation where you might need a little bit more, so let's just say climate changes and resilient infrastructure has definitely been a huge topic of structural engineers. So everyone in the background from their response has been beefing up their structures or analyzing it in 2 different ways. So on this design also included, and this might be way more information than what you need on your question, but every bridge that goes through the DOT's office also has to have an independent checker. So so I designed it, and then someone else designed it too. We verified numbers together, and we said, well, it could be beefed up more. And I went, actually, you're completely right. I'm going to beef up the exterior deck, and that was on purpose. That was a design change. Or if I think on one bridge, I think it was Islands Expressway, we decided that we should beef up our structure more and then analyze it in more of a finite level, just because we have hurricanes, we have seismic, we have poor soil, the geotech is scared. We have a lot going on. Also, we have flood insurance claims and everything else. You want to make sure that you're providing something to the public that will work through its lifetime and then some. Does that answer your question? That's a lot of
Yeah,
extra.
it makes sense. Yeah.
Okay, that's good.
And I'm gonna stop recording so students feel like they can answer the